Today we're going to take a look at solving a problem like the one that I've got shown on the screen here using SolidWorks simulation. Specifically, what we're going to try to find are the reactions between the various parts in the setup. We're going to try to find the shearing stress in a particular segment, the segment AB over here. And we're going to find the flexural stress in this member CED right here, right at the, well, it'll probably have its max right there at location E. So there might be a few other things that I'll show you how to find while we're doing this SolidWorks simulation study. Just to kind of mention them, I did another video where I showed how to build all of the parts in SolidWorks, how to actually, model those parts in SolidWorks so that we could use them for this simulation. And I also have done a lecture where I took this assembly and did hand calculations to figure out those stresses I mentioned, as well as, I haven't mentioned yet, we figured out how far this little assembly would deflect under this load of 20 pounds. And so we're going to try to check to see if we can get the similar results out of SolidWorks. So let's get into that. So I've got SolidWorks open here. I'm using SolidWorks 2018. And what we need to do first here is open the parts that we have just modeled. So one of those is this Swaybar piece. So I'll get that opening. Go ahead and open these other pieces as well. The rocker, that's kind of what I named that little lever that's, swings back and forth on the fulcrum. We have this other part that's named the larger bushing. These are going to kind of take the places of those pillow blocks. I didn't really mention them just now, but at A and at B we have these special kind of bearings that allow angular movement in any direction. And so to kind of simulate that in this SolidWorks technique, I'm going to use these little bushings that I modeled to be part of the system. All right, and then let's see here. I think I've got everything but the smaller bushing, so I'll go ahead and open that as well. And the reason I need a second bushing there is that you may notice on the original figure that the rods are not the same diameter. So we have a 1/2 inch rod that goes around here, as well as a 3/8 inch rod that goes across right here. And we're going to load with 20 pounds at point D. All right, so what we need to do is start an assembly, because we actually need to put these pieces together. So I'm going to go into New, Assembly. All right, and once I open this new assembly, a lot of times it just defaults to just asking you, hey, what do you want in your new assembly? And so I've got this Swaybar. That's kind of the main piece that we kind of think of maybe as the main piece. But what else do I have that I want in here? Well, it looks like it didn't actually open my rocker. Let me actually get that opening as well. Okay, because that's the kind of the first piece I want to manipulate and put into this assembly with the Swaybar. All right, so go back up into the window menu right here and choose this assembly that I've now started. And now that I've got that, there's this tab here that says Assembly, and I'm going to insert more components. And I want to insert this rocker. Okay. And so now that I've got that rocker in place, let me just kind of take a look at where it really is at by looking at a couple of views. Okay. All right. And so let me go back to a diametric view. And the first thing I want to do is start mating this component with my Swaybar component. And you might remember when we modeled this this part, there's a little dimple underneath this thing, and I could kind of show it to you there, but I don't have to necessarily look at that dimple in order to be able to select it for a mate, because I'm going to want to mate this little sphere in that dimple. All I have to do is use this really handy feature that's called Select Other. And it basically allows you to kind of have X-ray vision and view right through the material and find faces or other features that are going to be behind what you actually would see. Okay, and so if you kind of look through this little menu, this is what I'm looking for right there. That's, you know, maybe I should zoom in a little bit here. I'm looking for that piece right there because I want to mate that dimple that's on the underside right there with this piece right here. So I'm going to hit mate, and since I selected that dimple, right, it's already in my little list of selections, and so I need to now pick this face as another selection, and you might see there it automatically chose concentric as the type of mate, and that is correct. That's what I want to use. All right, so now I've got one mate that has now been established. Okay, now one of the things that I a lot of times do here is if that first mate that I used ends up putting this thing too close to being, you know, where it needed to be already. I don't know exactly why, but it seems like, it looks to me like sometimes that messes up how exactly the mate forms. So someday maybe I'll figure that out. But what I a lot of times do is I take a second and I just sort of rotate the member a little bit so that the mates that I establish actually drive where it ends up being located. So now what I'm going to do is, again, take a look at this and you know, maybe rotate this down a little bit like this, and put it back in this view. And this will give me a chance to apply another mate that's going to establish where this thing is located. So I'll use the same technique I did before. I'll use select other to pick the dimple that's underneath there, right? And it looks like that's it right there. Okay, see that little dimple showed up? And I'm going to take that and mate it with this piece right here. Okay, so far so good. Now there's another kind of position that this thing may or may not have automatically found, and it is an angular position, and you might be able to see that by looking at this thing from this side. Okay, this is probably not the exact angular position that we were thinking that we might want, and so what I'm going to do is establish another constraint, another mate, right, that basically makes these two faces right here be parallel with each other. All right, so I'm going to again use this select other. I'm going to pick that underside face right there as well as this next face. Okay, now what it automatically does is it thinks that I want to use a coincident mate. That isn't exactly what I want to do. Instead, I want to use a parallel mate. And that sets those up to be parallel with one another. All right, so that kind of sets up all of those mates. Okay. The next thing that we need to do is get our bushings in there, and these bushings need to be located at their proper locations. So let me put in one of these things, insert components, larger bushing. Okay, and I'll put that right here, and I'll kind of rotate this around and see if I can pick a couple of edges here that I want this thing to align properly down the axis of this rod, but also align you know, radially correctly. And one way to do that is to pick this little edge right here and this little edge right here. And if I pick those two and mate them with a coincident mate, then that actually perfectly sets up where I want that bushing to be. Okay, so there's that. Now what I want to do is another one of those components, another larger bushing that I put over here. Okay, rotate it a little bit. Now I pick this edge and this edge, just like I did before. We're going to mate that with another coincident mate. All right, we've almost got all of this assembly put together in the proper way. The last piece we need is the smaller bushing. Okay, now the smaller bushing is going to require that we mate it a little bit differently. Okay, so we're not going to use an edge because we don't have another edge to make it coincident with. So instead we're going to take this inside face and we're going to mate it with that rod with a concentric mate. Okay. All right, we have one more mate that we probably need to do, and that is we need to actually locate this piece, this little bushing right here, properly down the length of this assembly. In case we don't remember, it was located so that it was 5 inches from the middle of the contact at D to the middle of where it's supported at E. And you can go back and confirm that I'm not lying to you if you want, but this rod right here is a 1/2 inch wide and this bushing is a 1/2 inch wide. So basically that means to get to the middle I would space over by a 1/4 inch on this rod right here, and to get to the middle of this rod I would go a 1/2 inch from one edge. That means that if I make a 5 inch spacing from the end of this rod to this face right here, that gives me that 5 inches that I'm looking for. All right, so rotate this a little bit and I'm going to apply this mate. Okay. It'll default to say, hey, do you want those to be coincident? No, I don't want it to be coincident. I want them to be at a particular distance. And it gives you a chance to enter that distance right here. So I put in 5. I've got it default units to be inches. So it correctly interprets that to be 5 inches from the end. Which also, just to reiterate the fact, that's 5 inches from the center of the little spherical mate that I've got right there to the center of the bushing. And that's exactly what I want. Okay. Those are all the mates that I need to make for this body. Let me get it back into a position that makes it easy for us to view. Quick note that I need to make. We are about to go into the simulation portion of SolidWorks. I have the tab already in my instance of SolidWorks right here. Some of you may not have that simulation tab already in SolidWorks, and if you don't, you can get it by going to the SolidWorks add-ins little deal right here, or you can go into Tools and Add-ins. Many of you may find that you have to enable the ability to use the simulation tools that I'm about to use. Hopefully you have them installed. It is possible to do a SolidWorks install without those tools installed, and if that's the case, you'll actually need to get them installed before you can enable them as an add-in. All right, so what we want to do here is go to the simulation tab, and another note I need to make is, we'll start a new study. The type of study we're going to do is a static study, so we'll do that. But the note that I need to make is all those mates that we just established for the assembly, those mates are good for establishing the initial positioning of everything in the assembly. Those do not define how the assembly will continue to interact with itself during the loading and subsequent deformation of the assembly. We need to do that separately in the how we set up this simulation. Okay, so anyway, I've got this static, it's called static 1 down here in the bottom tabs. This simulation is started. And one way of doing these is to basically just move across the, it kind of almost guides you with the order that it has all these different items that you might want to do up along the top. So it's not hard just to start by saying, what kind of material do you want this to act like? And they have a little database of materials built into SolidWorks that we can choose from. You might remember over here that these were steel. And if you're not given anything else as far as guidance on what kind of material it is, most steels have very similar elastic modulus, which is kind of the big thing that we care about, and modulus of rigidity and that kind of thing. And so we can take a look at this. We have alloy steel as one of them right here. We can kind of look through the list a little bit if we want to. They all have slightly different, but they're all kind of similar in terms of the elastic modulus. So let me go up here. I think I'm going to use the 1020 steel cold rolled right there, and hit apply, and then hit close. Okay, and what that does is it now has established the properties of that 1020 cold rolled steel for this simulation. All right, the next thing we want to do is go in here and establish some fixtures. Now, you can do it up here along this menu along the top. I actually prefer to do all of this in the little tree that's over here on the left. It's just kind of how I learned to do it to begin with. So I'm going to use these over here, but you can just as easily use the buttons up along the top. One thing that we need to do before we start establishing our fixtures, I need to show you something that defaults whenever you take an assembly and you get ready to run a simulation on it. It typically defaults to thinking that you want all of your parts that are part of your assembly to act like they are literally stuck together rigidly at the locations where they touch. That's not really what we want. So how you know that is it uses this little global contact and then says in parentheses bonded. The way to interpret that is as if they are all literally kind of made to be one piece in the simulation, and that's not what we want for this simulation. So the first thing I want to do is just delete that global contact. Okay. All right. Now, the next one up here was Fixtures Advisor. You can get that down here as well under Fixtures. It gives you a bunch of different options here, and you can certainly play with all of those. I'm going to go immediately into Advanced Fixtures, because inside of Advanced Fixtures, it gives us some choices about some special types of faces that we can get fixed, get to where they have a position established. And I'm going to choose this spherical faces because where we want to apply these fixed locations, not surprisingly, are on each of these spots where we are holding the assembly in a fixed location. Here's the thing though, we're holding them in a fixed position, but we want them to be able to move angularly however they want to. The way you can do that on these spherical faces is by establishing that all of the radial positioning of the material on the outer face of these parts is going to stay at that exact radius relative to the center, and implied with that is that the center is also not going to move. Okay, I know that may not seem intuitive, but the way we can get that done is, well, let me first pick the faces that I want to do it to. So I want to do it to these three faces, right? I want to make sure that those three faces are constrained from moving around, but are not constrained angularly. The way we do that is down here, there's three different kind of options. One of them says radial, and then you've got two sort of tangential directions. I want to leave those tangential directions free, but specify that I have zero shifting in the radius positioning of all of the surface of these parts. All right, and that's all I have to do at that stage. All right, so we now have our constraints established, our they call them these fixtures, right? So that these faces right here aren't allowed to move. The next thing on our agenda is to define our external loads. Before I get to that, I frequently forget that it's important for us to save frequently along the way. So let's go ahead and save this thing. And let's save it as, let's see, I'm going to save it under this example that I'm working on right here. And we'll just call this the Swaybar assembly. Okay. So now we'll get into our external loads, and just to remind ourselves what we're trying to do there, we're trying to take a 20-pound load and place it onto bar AD above where that spherical contact is happening between bar AD and CED over here. Well, some of you who've tried to do this before know this is a little bit tricky because SolidWorks wants you to pick some sort of an entity to actually apply that load to, and we don't have anything that's already sort of built right here that allows us to just put that force right where we want it and not, you know, maybe everywhere along a whole line or something like that. So there's some tricky things you can do that allow you to get that done, but I'm going to show you one that's, you know, very helpful in a lot of cases. It involves taking a surface and splitting it. That's why we actually made this little sketch. Those of you who looked at the other video where I made these parts, I left a little sketch right here, and that's going to be very useful for us to do these this particular load we're trying to do. So under External Loads Advisor, we can go to Force, and you might notice in this thing we've got this Split tab, and the Split tab has a couple of items. One of them is a sketch, and one of them is a face. And it allows you to take the sketch and project it onto the face and create kind of a separate little entity of that surface that is split apart from the rest without having an actual geometry change or difference. Okay, so in this little box right here, I want to pick this sketch, and right here I'm going to pick this surface. And once you've picked those two things, you can hit this button that says Create Split. And what you see happen there is it has now taken that sketch and projected it up onto this surface, and it allows us now under the other tab that says Type, it allows you to define that as being where this force is going to be applied, right? It's on this little surface. One of the things, though, we don't want it to be normal to that surface. We want it to be in a particular direction. Okay, and we can define that direction. Probably in my mind, probably the easiest way to do it is to make it in a direction that's normal to a face that's under here. So I'm going to again use this Select Other, if I can. Select Other. And I'm going to pick that face right there. I'm going to use that as my reference item in order to pick a direction that's basically normal to that face. Down here you can pick what kind of units you want to use, and so I'm going to use pounds, you know, an English system of units, and it gives you 3 different directions you can apply for your force on that face, and I want to use the normal direction. Okay, and it gives you a little hint with those arrows. It says, hey, the direction is going to be is downward, which is good. That's what I want to do. And here I can enter how much force that is, 20 pounds. All right. And I think that sets me up for my external load that's going to be applied to this part. Okay, so that gets that stuff done. One thing that a big thing that we haven't done yet is defined how the parts are going to interact with each other. And so what I'm going to do for that, you can see up here there's a Connections Advisor, but there's also down here there's this tab or an item in this tree that says Connections. You can actually define these things that are called contact sets. Now, I like to use these. These are, well, we'll say it this way. They do one of the best jobs of modeling how a real part will really interact with another real part. That's what it's good at. What it's not so good at is being computationally easy, okay? Because once you have established these sort of contact constraints, there's a lot of computation that has to be done with the contact between one part and another part. They're very easy to use as long as you have defined all of your geometry correctly, because they are actually trying to compute what would really happen if a real part with these properties really interacted with another part with some kind of properties, and it actually tries to figure out those contact forces and stresses and that kind of thing. What you do is you can pick this no penetration. That's what will most of the time use for this. It's basically saying this part's not allowed to penetrate the other part. And so I'm going to pick, for one face where no penetration is allowed to occur, I'm going to pick that face right there of the Swaybar, right? It's that little dimple. And I'm going to pick as my other face the little ball, okay? And another thing I'm going to do for this particular one, it gives you the option of establishing some of them that might have a little bit of friction, which basically resists motion tangent to the surfaces that contact each other. I'm going to enable that friction on this one. The reason I'm doing that is that friction will actually help to stabilize rotation of this rod right here around its axis. Okay, so that's why I'm picking friction for that particular contact. All right, what other kind of contact should we deal with? Well, we have one right here. We need to make a no penetration condition between the bushing and the rod that's going through the bushing. So to do that, I will do the select other technique again, and I'm going to pick that face right there. It's inside of the bushing, and I'm going to say that it cannot be penetrated by the face of the actual rod that's going through it. Okay. So I've got those two things picked. I'm going to go to contact sets. You can see, well, you don't really want to do it that way. We pick that face of the smaller one. Now I pick the face of, or excuse me, of the inside one. Now I pick the face of the rod that goes through it. And we're going to just accept that. Okay, so what we have so far here is the first contact set that I did, and then now this contact set. And we'll just go around. This one is very similar to that first one we did. Okay, I can pick that face right there and go into contact sets. And I'm going to define those two faces as not being able to penetrate. I'm not going to define any friction for this one because I don't need to. The other one will be enough to stabilize axial rotation, which in real life that wouldn't actually be a concern, but in here it helps if you make it to where that things cannot just sort of move because nothing has friction. All right, so accept that. We have two more that we need to do because we need to make sure that this bushing right here can't be penetrated by the rod that goes through it. All right. And so I'm going to pick that face right there and create a contact set between that and this part. Now for this one, I'm going to also establish a friction factor here, and I'm going to increase it just a little bit. A reason for this is that I feel like this one has more of a chance that it is going to need to react down the axis, maybe some small amount of force, and so I'm going to make it a little bit more friction between the parts. All right, so I'm going to let that sit. And then I'll do the last one over here. So again, I'll select that face right there. And I'm going to establish that with this contact set between it and this rod. Okay. So I think I should have, for my entire assembly, I should have 1, 2, 3, 4, 5 contact sets. And I think I've got them all set up with this now. All right, so we're getting close. Tell you what I'm going to do at this point is I'm going to save, just so I don't lose my stuff. And what I want to do now is to do these simulations. What it does is it takes the material and it splits it up into small pieces, small enough pieces so that each piece has a pretty simple way that it actually will deform and change and, you know, have stresses in it. And then you take a bunch of those pieces, usually they're tetrahedrons, and you stack them all up together to basically approximate the geometry of what we are really trying to analyze. And that process is called meshing. You basically are making this, you know, spatial mesh out of the part that we're looking at. So I'm going to do that here. What we can do is, you know, one place to get to it is up here. You can go to create mesh, and this is really great where it just has a little slider. I usually try to go as fine as I can until something fails. So I'm going to go all the way to the fine end of that setting. You can get more deep into exactly how to mesh this, but I've tried this before and it seemed like it worked okay. So I'm just going to take this and move it all the way to the fine end. And you can actually see what that mesh looks like physically once it gets to the end. You can zoom in and you can see all the little tetrahedrons that are forming this material. And you can even see right here the split that you did actually becomes kind of a boundary line in the mesh, that's pretty neat. Okay, so this is our assembly that we're going to try to model. Okay. I'm trying to get it in a particular spot on my screen here. There we go. The mesh is done, and so what we can do now is actually run the study. It can take a little while to do, sometimes 10 minutes, sometimes 20, sometimes maybe an hour. So what I'm going to do is go up here under the run this study. And if you just click on it, it will start trying to solve this. It puts up this little window and it tries to give you a little bit of information. You can actually tell it to give you more information. Okay, so I'm going to take that and put it over here. It actually even gives you another button there where it says convergence plot. And so if you want to see how the solution process is going, you can actually take this thing and let it, you know, kind of show you what's going on. Do you know what it means? Well, a lot of times no, you won't really necessarily know what it means. But what you can see there is that there are some parameters that are being maybe, you know, optimized. A lot of times the numerical solution behind the scenes has a very guess and check type of a structure to it. And so that's what it's doing, is essentially doing this guess and check. And as it does that, it gets better and better solutions. And at some point, once the solution gets good enough, we'll say it has converged on a good solution. So that's what that word converge means in this context. Okay. So we'll just give it a couple minutes here to try to finish. You see there what it's trying to do is solve for these contact constraints. So that is a big piece of what it has to do, is figure out how these parts are going to interact with one another. And if you can manage to do your models where they don't have those contact constraints, there's other kind of constraints you can use. One of them I encourage you to look at is called a bearing constraint, or a bearing fixture, or a bearing connection. Those are a little bit more simple numerically to define how one part interacts with another part, or how a part interacts with a support. So you might want to check those out. What I'm doing here, though, is probably the most realistic in terms of how these parts would really interact with a real part. You know, so that's why I like to use these as my starting point. But, you know, if you need it to be less computationally intense, you know, which frequently will happen if you end up with a assembly that's more large, with a large number of parts, you might need to actually give your computer a little bit better chance of being able to solve all of that. And so anyway, it's good to know about some of those other ways that you might think about doing this if you need to lighten the load a little bit for your computer. All right, so it looks like the solution has converged, and what it shows you immediately here is, it actually put a little label up on top of here to let you know what it's telling you. What it's telling you in this case is the von Mises stress, which is a way of combining multiple components of stress applied to a little element of material into one number that you can compare against a yielding stress or yielding strength for a particular type of material. A couple things about this. I'm going to maybe get back to the stress question, but what I'd like to do is use the hand solution that we've already done to kind of go through and check the results and see, are we similar to what the results were with our hand solution, and maybe we can, if they're not similar, we can discuss those also. So for the solution we did here, what was the first part we did? Okay. The first part we did was what I called a static analysis, where we did some free body diagrams and figured out how much force actually existed between these different parts. And two of the most interesting forces to us for that process were this interaction force between the Swaybar and the rocker. I called it FD, and another one at C called FC, right? Those are those interaction forces. And we did these equations, and we figured out that the force between the two parts at D was going to be 11.667, and the interaction force at C was going to be 8.333 pounds. Let's see what SolidWorks says. Here's how you get to that. What you can do is, under the results item in this list over here, one of the things you can do is this thing. It says list result force. Okay, and it gives you this little interaction window on the left. And a couple of things you can do here. It gives you a lot of choices, but the one I'm interested in is this thing called a free body force. Okay, basically this is what the same force that you would think of as being on a free body diagram, and that's very helpful. So I'm going to pick that, and then under here I'm going to pick English so that it gives us units that we're comfortable with looking at. And so let's check out, this would be similar to the point D that I had on my hand solution. Okay, and if I pick this surface right here, I hit update, what it will show you is some force. Now, this actually has happened to me before. I'm not very happy with this particular result. Why do you think I'm not happy with this result? Well, I don't like that it turns out to be 23.4 pounds. And the reason I don't like that is that's not right? It goes, 11.667. I find it very interesting that it's right at about double of what it should be. And I tell you, I don't know why it did that. This has done this to me before. I don't know why it did it, but I'll show you what I did to fix it. What I did to fix it was I went back in here. So I'm going to go in here and delete this force. And then put it on again. Okay. And we're going to go in a selected direction. We're going to go with English units. The selected direction is going to be based on this face right here. We're going to go normal to that face at a value of 20 pounds. And we're going to pick this spot right here. That's not what I wanted. I want to pick the face. There we go. All right. And I think that sets that up. And what I need to do now is run it one more time. All right, that looks more like it. I don't know what causes SolidWorks to do that sometimes, but it does sometimes. So what you see over here is that we have a number that's a lot closer to the 11 KSI that I happen to know from the hand solution is probably closer to what it should have. So let's pick back up where we were and try to look and see if we have reaction forces like what we were expecting according to our hand calculation. To do that under the results, you can go under the list result force. You can do a free body force and pick a particular face that you want that free body force for. Instead of SI units, I want this in US units, so I'm going to pick that. And I'm going to hit update. And it says that we're going to have a downward force of 11.7 pounds. Does that jive with what we had over here? Very much so, right? Downward force of 11.7 or so pounds. Okay? Matter of fact, over here it gives you a more accurate number, 11.679, so very close to what we had calculated by hand. Cool. Can we do this for any other spots? So I can clear selections, you know, and check it out over here. This face, let's see how much of a free body force I have acting on that face. So now that I've got that picked, I can hit update. 8.32. That's also very close to what we found whenever we did this calculation by hand, right? 8.33. Okay, so that is also helpful. You know, we can have a little bit of confidence that what we did with SolidWorks here is accurate because it matches what we found using our hand calculation. Any other places we care about? Well, yeah, maybe so. We can check and see for this part how much of a reaction is happening at that surface. That was something that we used when it came to figure out the bending stress that happened in this rod. You know, we needed to know what the reaction was here, so we can also get it to tell us that. Okay. Over here, 20.068, here says 20.1, close enough, right? 20 pounds of upward reaction force happening on that surface. And I know that's not right here, but that's, if I scroll down a little bit, we had to figure out what this reaction was right here in the middle. Maybe we never did actually say what it was, but it was 20 pounds of reaction that happened here in the middle. Between negative 11.667 and positive 8.33. All right, so we're in good shape in terms of the amount of reaction that I have on the various supports. And so that's a neat thing that we can check with SolidWorks. What else might we care about? Well, let's see. In our solution here, the next thing that we found was the shearing stress in segment AB. Okay, and go back up here. AB was this piece that went in between these two sides. So it should have relatively constant shearing stress in that segment. So let's figure out what that shearing stress might be. It's hard to find that shearing stress directly with this von Mises stress. And so what we can do is under this stress, we can actually go in and edit the definition. And instead of it telling us this von Mises stress, we can tell it another kind of stress that we would like to see. And what I'm going to suggest we look at is this thing that they call TXY. Okay. And if I hit, yep, that's what I want to see, then what it shows you is basically, you know, you see your XY plane, it's showing you that shear in that XY plane. And, all right, it's not actually up in the red zone up there. Tell you what, I'm going to, instead of using the XY plane, we can probably do it with the XZ plane as well. And it might actually give us, see, the highest number here is probably being affected by some concentrations. Matter of fact, you can probably see it right in here where it gets really high amount of shear. That's not really what we calculated when we did our hand calculation. So we can probably avoid some of that on the inside of this curve right here if we choose to show the stress in the XZ plane. So I'm going to go ahead and edit that definition and choose TXZ. And now it'll show it those numbers at the top and the bottom. And it ends up telling us here, it goes from positive on the bottom side down here, positive 2.809 up to negative 2.802 or so up on the top side up here. And that's exactly what you would expect for the shears that we're talking about there. Okay, so let me check that against what we've calculated in our hand calculations, right here, 2716.24. So basically 2.7 KSI, and SolidWorks says about 2.8 KSI. And again, that might be a little bit tricky. There might be some concentrations somewhere that we're not accounting for. We're definitely right in that zone of being, you know, very much in line with what we calculated with our hand calculations. Before I leave this, I'm going to show you another thing here real quick. One of the things that SolidWorks can do is show you stress tensors. And a stress tensor is this kind of strange thing for people to get when they're looking at it from a mathematical perspective and they're thinking about it from the perspective of it being like a matrix or something like that. I want to show you physically what we're talking about with this stress tensor idea. And you can do it by essentially showing a little element of material that has been rotated a little bit. And, you know, when it's rotated, when the stress element is rotated a little bit, then you can actually see where these stresses are being applied to it. It can be rotated to where it's oriented along its principal axes, and then you can see what the magnitudes are of those principal stresses. And that gives you an idea of what the actual stress state and direction and all that is at a particular point. To do that, before I actually use these advanced options I opened up just now, let's go back into von Mises stress, because under this von Mises stress, it tells you this option here of show as tensor plot. Okay? And I'm going to do that. Now what it's showing you here, it gives you a few little edges so you can kind of orient yourself. What it's showing you here are these little patches of material. And if you look at these patches of material, this is one that's like right on the surface of the shaft, and it's telling you that you have these principal stresses that are oriented at about a 45-degree angle relative to the axis of the rod. Well, that makes sense because if you have a state of pure shear, which is approximately what that rod is that goes through the middle of these bearings, then, you know, your stress element is oriented at a 45-degree angle relative to the the principal directions for that element. You might also notice that this is basically a state of plane stress because we don't have any other arrows acting other than these ones that act in plane. Let me try to show you a counter example where it's more than that. Okay, here's one right here. This one right here, well, maybe that's not the best one. Some of these you can actually see 3 arrows. Yeah, let's see. Maybe I'll look at some of these down here. There you can see this is like a uniaxial state of stress because you have a really strong element of stress that happens down the axis of the member where it's bending and really no other components of stress. So that's kind of interesting. Although this one right here, you see a little bit, yeah, there's one. There's one where you can see 3 different arrows, even though you have one real strong direction and a little tiny bit in another direction. I'm trying to find a better example of one where you see 3. Maybe down in here somewhere. There's a good one, right there. Okay, not a high amount of stress, but it shows you that you have, you know, two directions that have tensile stress and then one direction that has compressive stress on a little element of material that's right down there somewhere. All right, don't want to belabor that too much, but it does give you a way of visualizing the actual, you know, the idea of principal stresses and how they can act in multiple, or that basically you can find this direction that they act, and then you can boil it down to just normal stresses along that set of directions. All right, I'm going to go back here to edit this definition again and take it, because it's hard to see it all if you leave it as a tensor plot. Okay. What else were we supposed to find in our hand calculation? Because right now we just verified that SolidWorks has a pretty similar answer for my shearing stress in segment AB. Okay. What about normal stress? We took a peek at that just now with our stress tensor, but what about this normal stress in member CED? That was this member right here, and we said your maximum stress probably occurs right in the middle of that rod. Looks like we're confirming that here with the SolidWorks deal, and it says it should be about 11 KSI, 11.27 KSI or so. Let's see what this says. Now here's the thing. Von Mises is interesting, and it's probably going to be very close in value to what it, you know, what I really want to know, what we did our hand calculation based on, but it's not exactly what that value is going to be. If I want to get a better idea of, you know, exactly what I'm talking about with respect to the stresses on this surface right here, what I probably want to do is go in and edit this definition and have it give me the stress along the normal stress along the x direction. Okay, and when I do that, two things show up. One is it shows you that you have a positive stress, tensile stress along the top, and then you have a compressive stress along the bottom. But then you can take a look at these values, okay? 1.114 times 10 to the fourth, all right? That's basically 11.14 KSI, all right? And if we go into the solution here, right, 11.26 versus in here says 11.14, very, very close. So this gives me confidence that things went well with respect to the simulation. You know, which one do you trust, your hand calculations, the simulation? Really, it's a matter of, you know, you have to make assumptions for both, right? You have to make assumptions for your hand calculation, and you have to make assumptions for your simulation. They are good to work in tandem. It's hard to say which one should be definitive, all right? So, all right, so what should we do next? Go in and see what was it we were supposed to find here. Okay, the deflections, right? We're supposed to find the change in position of point D, all right? Well, I'll tell you what, let's actually take a moment and talk about deflections on this. I'll show you a couple of cool things. First of all, I'll tell you what, I'm going to move this back to being a von Mises stress first. All right, so the first thing I want to show you is you can actually animate this assembly, and it'll show you how it will begin to deform, okay, under the load that you apply. And this is actually really helpful because it helps you to validate your results, right? If your model ends up doing something totally different than what you would have predicted it should have looked like, it gives you some ideas that maybe you didn't set up your constraints properly, right? Maybe something went wrong with how you set it up or how it's solved. And so what you can do here is you can kind of inspect how this thing is deflecting and say, does that look like it, how it should, in theory, be deflecting? Sometimes, though, it's kind of hard to see exactly how it's deflecting. And so what I want to show you here is I want to show you that you can change kind of a multiplication, a magnifier effect, maybe we'll call it that, right? How much more does it show the deformations than what they actually are? Right now it has true scale selected as far as what the deformed shape looks like. And if you go to this automatic, or you can do a user-defined one as well and enter kind of a multiplication factor of how much the deformations show up as. If you go to automatic, it kind of comes up with something that helps you see what the deformations look like generally a little bit better. Okay. And that's what they look like. And now we can kind of take a look at this and see, does this seem like it makes sense? You view like a front view and you say, is that what that member should be doing? And I'm going to pick out a few things. One is, look at this point right here. You can see that ball joint is allowing there to be some angular movement, one piece relative to the other. That's important because that tells you that it's actually operating properly with respect to those two pieces having freedom to move relative to each other. Similar thing here, right? There's some angle right there. Let me actually show you another one that's kind of interesting. If you view it from the side, you can actually see a little bit of the curvature of these elements right here, right? So that gives you some confidence that that is behaving how we thought it was going to behave, right? And to kind of confirm that, you can go back in here. We thought that these pieces were going to flex a little bit, and you see there's a little bit of starting out angle, but then a little bit more of a curvature after that starting out angle. Okay. Here's another interesting thing I was going to show you is the angle of this end of this piece basically still corresponds with the angle down here. That's that friction factor that I applied on the ball on the opposite end, but not on this ball. That friction factor is stabilizing the rotation of that element, of that member, and so because it has that friction factor and no other friction anywhere else, it basically is just going to move angularly down its axis so that it kind of matches whatever this member is that comes in right here. All right, so kind of the general shape of the deformation seems like it makes sense, and that gives us some confidence that our reasoning was probably okay on our hand solution, and it looks like our reasoning's okay. I mean, it all makes sense as far as how it looks like it would deform. Actually, I'll show you one other thing before I move off of this point. You might remember that we had that angle, I think I called it theta E. You can really see it here where there's this angle of kind of how far it has rotated at that support, and that could kind of be defined as that theta E. Okay, all that's great in terms of how far, or how it looks like it's generally deflecting. Okay, once I've kind of inspected that, a lot of times I like to go back in and say I want to see the true, how much does it really deflect, because I don't want to start convincing myself that it's really deflecting as far as all of that. Okay, but what we want to know is the amount of deflection correct? So it gives you another couple of items in this results tree. And right now the one that's bolded is the one that I'm showing. It says stress. I can go in here and show displacement instead of stress. Okay, and that's what it's now showing here, is how far has the thing displaced. And you can do fun things like animate that, if you want to see how it's deforming. You can actually see that. But you see that the furthest down deflection that we have is over here, right? And it says, and of course, it's defined in millimeters right now. I don't particularly like that. Let me go in and change this definition because I want it to match my units. So I want to change this into inches. Okay. And it says here 7.839 times 10 to the minus 2, which is basically 0.07839. And that's how far it's it's deflecting over here on this end. Does that match up with what we had in our simulation, or excuse me, in our hand calculation 0.07404 relative to 0.07839. Pretty close. Of course, you know, a couple things that are different between our simulation and what we did with our hand calculation. We assumed that these bearings were right at the kind of the bend point right there. That could actually lead to a little bit more deflection, which is what we're seeing here. That's a reasonable guess in terms of what might be causing a little bit more deflection in this case. Let me show you this too for the displacement. Just like von Mises stress is this sort of one number that tells you how close you are to failing the material, this deflection displacement that we're seeing right here is just how far did it move in any old direction, right? You can change the definition of that and figure out how far it moved in a particular direction, right? So instead of being this resultant displacement, we can check and see how far things moved, say, in the y direction. Okay. And what you see there is that we deformed downward by that 7.839 that we said a second ago down on this end. But on this end, where it's red, it means we're deflecting up by 4.78, I say 0.0478 or so inches. Does that jive with what we have? 0.0475. Very, very close with what we would have predicted using our hand calculations. Another thing to note is I didn't do anything to try to make sure that our elastic modulus was exactly what we used. You know, elastic modulus as well as modulus of rigidity. I didn't, you know, double check to make sure we were exactly the same, but they are both steels, and so they're going to be very, very close to each other. The numbers I used in my hand calculation versus the ones that are built into SolidWorks. So I think that just about covers the things that I wanted you to see with respect to analyzing these things. I'll tell you what, I'm going to show you one more thing. We'll do this, you know, exaggerated displacement, and then I'll animate it. Right? It kind of gives you this idea of what it looks like as it deforms. Okay. Well, I hope this helps you get started if you're trying to do an analysis using SolidWorks of a little assembly of parts like this and try to get accurate support, you know, reactions as well as reactions between the different parts. So I hope that's been helpful, and you know, I hope you continue to watch my channel. I appreciate you watching this.